A decade has passed since the Academy of Medicine, Engineering, and Science of Texas began recognizing the achievements of Texas-based researchers. Their discoveries, innovations, and groundbreaking research are transforming their professions and improving the world we live in. This year, we celebrate 4 shining stars as part of the 10th anniversary of the 2016 Edith and Peter O'Donnell Awards. In recent years, digital technology has intensified the quest for human efficiency. As each new model tops the last, one wonders how far this can go. What does the epitome of technical efficiency look like? As it turns out, we don't have to look far for the ultimate in efficiency. It's all around us, in nature.
Nature is optimal. Nature wants to be optimal and waste as less energy as possible.
Dr. Alessio Feghali of the University of Texas at Austin has chosen to focus on the math found in nature to further the study of a concept that has intrigued mathematicians for centuries: optimal transport. The optimal transport problem, simply put, is, given a certain cost, what is the most efficient way to move an object from one place to another?
Basically, mathematicians have tried for a long time to understand whether there is really a way to transport resources from a place to another in the most efficient way. It's not clear that such a way exists. It's not clear whether one can compute it.
Optimal transport applies to a variety of fields, such as economics and urban planning, but it is also seen in nature. Specifically, Alessio and his team have focused on optimal transport as it pertains to the formation of crystals. Alessio and his team wanted to know what changes when you add energy to a crystal. For example, what happens when you change its temperature?
The simplest example could be take a crystal and start to heat the crystal. So this way you give some energy to the crystal, and the crystal will start to deform. And then you may ask, okay, how much the crystal is going to deform in terms of the energy I gave to it?
By comparing the original crystal shape to the crystal that has been heated, Alessio was able to identify nature's innate progress in moving the particles of the crystal from one place to another. Knowing how optimal transport works in nature has allowed Alessio and his team to help solve this historic math problem that can be found everywhere, even in meteorology.
What happens is the following. You have to think that clouds are made of particles, small particles of water. So if you want to understand how clouds evolve in time, what you do is that you say, okay, how does each particle evolve during time?
The more you know, mathematically speaking, about these equations, the more accurate and efficient your predictions become.
For the past year, Alessio has used his newfound understanding of how cloud particles move to create equations to predict cloud movement.
It turns out that if you look at how the cloud looks like, let's say at some fixed time, and then at some later time, and you look at how each particle has moved in time, then you discover that the particles have decided to move in an optimal way. So the way a particle moved has been in the cheapest possible way.
Equations developed by Alessio and his team could allow meteorologists to be more accurate and efficient in their weather forecasts, potentially improving advanced warning systems for severe weather. A true mathematician, Alessio is interested in solving all kinds of problems and finding the solutions in unlikely places.
In the mathematics, he's one of the best person in his generation around. I mean, I don't know how many you could compare with him right now.
Being a researcher is a complicated job, but it's probably the best job I could think of because you have to be creative, you need passion, of course, but basically your job is to find things that no one found before. It's a challenge, but it's also an enormous satisfaction once you succeed in what you're trying to do.
The art of printing goes back more than 500 years to the days of Johannes Gutenberg, who published a Bible that was the first book printed on movable type press in the West.
Hey, what are you working on?
Today, Dr. Van Truscott continues to advance the printing process, much like Gutenberg, with groundbreaking results.
When I was young, I would take apart watches,
my mom's appliances, which was probably not a good thing. But just wondering how things worked.
In 2002, Van brought her curiosity for how things worked and engineering background to molecular imprints, which was later acquired by Canon Technologies. The company was working to develop higher resolution, lower cost of ownership printing solutions for its customers. Van focused on improving the technology behind jet and flash imprint lithography.
Jet and flash imprint lithography is really a very high-tech version of a printing press. We essentially are able to print features incredibly small.
Here's some checkerboard wafers that Terry has imprinted.
The printers at Canon Technology are designed to print on a thin slice of semiconductor material, also known as a wafer. These wafers are used in the fabrication of integrated circuits and other micro devices. Van's lab was set up to refine and perfect the company's dispense method onto these wafers in order to gain more control over this printing process.
When I started here, we were using essentially a displacement pump, and we were putting down single large drops on order of microliters.
A microliter is 1/1,000,000th of a liter, or roughly the size of an average salt crystal.
The next thing that we're going to need to figure out is whether these electronics are compatible.
Van's objective was to create a drop-on-demand technology to dramatically decrease the size of these drops. Success would be revolutionary in the industry.
Well, she took the existing inkjet technology at the time and improved it in terms of making the drops smaller, faster, more accurately positioned. So right now we have inkjet systems which are clearly the most advanced in the world.
We have the only industrial inkjet that can dispense a picoliter, and it's actually in a tool for semiconductor applications.
To put a picoliter into context, there are several 100,000 picoliters in just a single raindrop.
Van and her associates were the first ones who came with totally new techniques of really putting on the surface of the disk minute droplets and putting them in a way so that they could create exactly what she wanted to achieve.
The applications range from improved computer chips, so your cell phones will work 10 times better than they do today, brighter, crisper displays. Nanopharmaceuticals is looking out more into the future, and also to look at improved solar cells and batteries.
This is an experimental design.
For Van, reaching this industry-changing goal was thrilling, but the journey was the biggest reward.
I had lots of moments of, I'm never gonna figure this out, I think. I would say you fail 80% of the time, but of that 20% of success, it's really gratifying. And even though you may be failing 80% of the time, even out of those failures, there are huge lessons to learn. And those are the things that I think have really helped to refine me as a person, as a researcher, and as a scientist.
Thanks to an innovative high school program, Dr. Josh Mendel got his first taste of working in a laboratory when he was just 15 years old. That experience propelled him into the world of molecular biology and gave him the passion for the field he carries with him today.
One of the things I've always loved about doing science for me is that it doesn't feel like a job. You know, it's something that I truly enjoy doing, and if you find a career, even at an early age, that you love to do, then you're going to want to stick to it and embrace it, and that's what I've had a chance to do.
Throughout his career, Josh has enjoyed focusing on new frontiers in microbiology, exploring the lesser-known aspects of the field. This led Josh to the study of non-coding microRNA, the tiniest of RNA molecules. Like DNA, RNA carries genetic information, but it is much more versatile than DNA, capable of performing numerous, diverse tasks in an organism.
So I have the inputs on here.
But to find out more about exactly how these molecules operate, Josh and his team had to first find a way to study them.
When I started my laboratory, there were very few tools available to study microRNA levels. One of the first things my laboratory did was build a tool that would allow us to measure the levels of hundreds of microRNAs simultaneously.
With that tool in hand, the team turned their focus to cancer cells. And when they started measuring the cell's microRNA levels, they discovered abnormalities. When Josh and his team studied microRNA levels in liver cells, they found that cells with cancer had much lower levels of microRNA than healthy cells.
We suspected that if we could restore the levels of that microRNA to its normal levels, then perhaps we could block the formation of those tumors. And so we developed a delivery vehicle that we could inject and deliver that microRNA to the tumors in the liver.
The results were groundbreaking.
What was really exciting was that the surrounding normal liver, even though it had also received the microRNA, was completely normal and fine. So the tumors had this selective sensitivity to the microRNA. How long is this going to grow for?
Josh did some of the pioneering work in the field, uncovering critical roles of microRNAs in cancer. He made mouse models of cancer and published a seminal paper showing that overexpression of one single microRNA could completely prevent liver cancer in this mouse model.
Or is that the 10% of that?
That type of work really opened the door to a number of investigators throughout the world to begin to further explore the role of microRNAs in cancer and other disease states.
Josh and his team's discovery has the potential to give doctors one more tool to combat cancer. And that idea has only fueled Dr. Mendel's drive to continue exploring biology's great unknown.
I think that the career that I have now is the career that I always dreamed of having, and the opportunities that we have now to work on scientific problems are really limited by our imagination and creativity, which is, I think, any scientist's dream.
From Star Trek
They have the cloaking device.
to Harry Potter,
That's an invisibility cloak. I'm invisible.
making an object invisible has long been a staple of fantasy and science fiction. But new research by Dr. Andre Alou in the field of metamaterials is bringing the idea of invisibility, or cloaking, closer to reality. We caught up with Andrea in Amsterdam while on sabbatical from his lab at the University of Texas.
At the optical lab. The scattering from an object is actually the reason why we see objects. When light illuminates an object, a portion of this energy gets scattered, reflected or diffused, and that's what our eyes detect. What we proved is that if you are able to design a suitable material that can scatter light with an opposite phase than the one scattered by the object, the interference between the two scattered waves can cancel the overall scattering of the cloaked object. And if you are able to do it for all angles, then the object becomes transparent.
Andrea and his team haven't yet created material that will make objects vanish before your eyes, but they have captured a lot of attention for successfully making objects invisible to radio waves.
Our group has shown the first prototype of a cloak for a 3D object in free space, and since then we've worked on many advances in this field.
Their focus has been on creating metamaterials to cloak radio antennas.
We build cloaks or flexible surfaces that can be put around an object to make it disappear from specific frequencies of excitation, essentially build a cloak of invisibility for objects of interest.
These radio antennas developed by Andrea can transmit and receive signals, but are also radio transparent.
So other antennas placed very nearby them or are not affected by the presence of these radio-transparent antennas.
Oftentimes, these antennas need to operate in very crowded environment, and some of the concepts he proposed would allow us to have more devices in a noisy environment without having them interfering with each other.
And that can improve radio communications, especially in crowded environments like an antenna array, the rooftop of a building or a ship or an airplane or a laptop, in which many antennas have to be placed nearby each other and there are many other objects that interfere.
Andrea and his team are also working on a technology that could potentially double the capacity of wireless networks, called full duplex communication.
Today, when we talk on a cell phone, we are using one frequency channel to transmit our signals, our voice, and another frequency channel to receive the signals from the radio base station. With this device, now we're able to do full duplex communications. We're able to transmit and receive at the same time on the same frequency. We were able to build isolators and circulators that are more complex three-port devices that allow to transmit and receive through the same device at the same time on the same frequency channel. This was highlighted on the cover of Science last year.
I have here this little sample.
With so much potential, it's no surprise that Andrea's innovations are being shared all around the world.
He's one of the best that UT system has to offer. And I think the work that he's done will truly have a potential to impact future technology.
The basic equations that govern everything that I do can be written like this. The field has exploded. Now metamaterials encompasses many different areas, not just electromagnetics, but many fields of science. It's a very exciting field of research.
Congratulations to all of this year's recipients of the Edith and Peter O'Donnell Awards.